In this video, we're going to talk about the point of diminishing return. So the point of diminishing return is a concept from economics, specifically the field of microeconomics. And it's the point of diminishing returns refers to the optimal level of capacity, where beyond that said point, every additional unit of production factor results in a smaller improvement in output. So we're trying to see where the rate of increase is the steepest. So we're not actually looking at the highest y value. We're looking at the steepest slope. And so if you look at this function, the slope is like increasing and it increases until we get to the point of inflection. And so they're saying the point of inflection is here. And then after this point, the slope no longer increases, it starts getting less and less, and the slope is decreasing. And so if you look at this graph in orange, this is the graph of the marginal. Remember, the marginal is the derivative. And when we're looking at the point of diminishing return, we're trying to figure out when is the marginal max? When is the rate of increase the highest? That's the point of diminishing return. And that happens at a point of inflection. So this point, this whatever this x value refers to, is where my function would be increasing the most, and that's considered the point of diminishing return. So as a summary of what it means, the point of diminishing returns refers to the optimal level of capacity, which is the inflection point of a return or production function. The law of diminishing returns states that beyond the optimal level of capacity, every additional unit of production factor will result in a smaller increase in output while keeping the other production factors constant. The point of diminishing returns appears where the marginal return or output is maximized and can be identified by taking the second derivative of the return or output function. So when we're doing the point of diminishing return, we are looking at when is the rate of increase the highest, because we generally with these problems will talk about functions that are increasing, but we want when is that highest, and that's called the point of diminishing return. And how we find that is by taking the second derivative and making sure, just to go back a second, so we find the point of diminishing return by finding the second derivative and making sure that my original function, whatever it is, so if I call it f, and we are going to find the second derivative where it's 0. And what should happen if we have a point of diminishing return is the second derivative should go from concave, or the second derivative should go from positive to negative. So that means my function was concave up, which means the slope is going to be increasing the whole time on that interval. And then we're looking at when the function is concave down. And so at a point of diminishing return, the function has to change from concave up to concave down. And the second derivative has to change from positive to negative. Now, I should have put the 0 here and not here. This point is whatever we get when we take f prime of x equals 0. And so this point is whatever this x value is when we take the second derivative and set it equal to 0. So let's look at an example. This is from the packet. It's on page 17 from Unit 2 packet. So it says a discount appliance store is selling 200 television sets monthly. If the store invests X thousand in an advertising campaign, the ad company estimates that sales will increase to, and this is my function. So this is the function for our sales. And so we have n of x equals 3x cubed minus 0.25x to the fourth plus 200. And they usually give me a domain for these problems. So I'm only looking at x values between 0 and 9. And they also include 0 and 9. So to find A, which says determine the point of diminishing returns, we are going to find the second derivative. To do that, we first have to find the first derivative. So we are going to take the derivative of 3x cubed. So we have 3 times 3, which is 9. And then we have x, and then we do 3 minus 1, which is 2. We're going to multiply 0.25 times 4, which would give me 1. And then 4 minus 1 is a 3. And then the derivative of a constant is 0. So we don't need that. Then I need to take the second derivative. So 9 times 2 is 18. And then I would have x, 2 minus 1 would be 1. So it would be x to the first, which we don't need to write. And then I would have negative 1 times 3, which is negative 3x to the second, because 3 minus 1 is 2. We are going to set this equal to 0 to find the x value that makes the second derivative 0. So for this, I need to factor. I'm going to factor out the GCF, the greatest common factor. So if I look at my numbers 18 and 3, 3 goes into both of them. And I look at x and x squared, the lowest x, or the lowest number of x's I have, is x to the first. And then I'm going to divide each of these by this 3x when I'm factoring. So 18 divided by 3 is 6. And x divided by x is 1, or they cancel, so I don't need to write it. And then 3 divided by 3 is 1. And then if I take out 1x from x squared, I just get 1x equals 0. And then I'm going to set each factor equal to 0 and then solve for x. So I get x equals 0, because in this case I would divide both sides by 3, and 0 divided by 3 is 0. And here I'm going to add the x to the other side, and I get x equals 6. So those are my two possible points of inflection. And I have to check it. Like, I have to figure out where my second derivative changes from positive to negative. So you can't just stop here. You have to check it by doing a sign chart. So I'm going to draw a sign chart for my second derivative. I'm going to put 0 and 6, and then I'm going to put my other endpoint, which is 9, because I'm just looking at these values. So I am going to plug in a value between 0 and 6 into my second derivative to figure out the sign. So let's just do 1. You can pick any number between 0 and 6. Just make sure you're not plugging in 0 or 6. It has to be between them. Okay, so I plug it into my second derivative. 18 times 1 is 18, minus 1 squared is 1, times 3 is 3. And then 18 minus 3 is 15. Okay, all I really care about is the sign. So you could also just plug it into the factored form. And you don't even have to solve it. You just have to figure out the sign. Like 3 times 1 is a positive. 6 minus 1 is a positive. A positive times a positive is a positive. I don't care about the numbers when I'm figuring out the sign chart. All I care about is the sign. So because n double prime is positive, it means it's concave up. And then I'm also going to try between 6 and 9. So again, any number between 6 and 9. So I could try 7 or 8. I mean, you can do decimals, but it's easier to do whole numbers. So I'm just going to do 7. Again, you can plug it either into the factored form or the original. And if you're a little shaky on factoring, then I'd plug it into the original so that you didn't, just in case if you made a mistake with factoring. But otherwise, it really doesn't matter. I usually plug it into the factored form because it's quicker for me to figure out if it's positive or negative. But for some of you, it might just be faster to just type it in the calculator for one of them. Really doesn't matter. But 3 times 7 is a positive, and then 6 minus 7 is a negative 1, so it's negative. And then a positive times a negative is a negative. Okay? And you're welcome to figure out that this is negative 21, but it really doesn't matter. All that matters is that you find the sign. So this is negative, which means this is concave down. I'll put zeros where the second derivative was 0. And so here is my point of inflection. And again, my second derivative has to change from positive to negative for it to be a point of diminishing return. Okay, so my point of diminishing return occurs at x equals 6. Okay, now since it says like a point, I'm actually going to find the entire point. So to do that, I plug 6 into my original function, n of x. So I'm going to find n of 6. Okay, and the function was, again, n of x, if I write it just so I don't have to scroll back up and down, was nx cubed minus 0.25 x to the 4th plus 200. And so I would have 3 times 6 cubed minus 0.25 times 6 to the 4th plus 200. And so I would evaluate that. So if I simplify that, I just typed it into my calculator to find it, I get 524. So the technical point is 6 times 524, or 6 comma 524. On the online homework, just pay attention to how they ask you to answer it, whether it's giving the x value or the actual point. So B says, explain what the point of diminishing return means in the context of this problem. And one thing we should just make sure, either by graphing or checking the first derivative, is my function should be increasing the whole time on my interval from 0 to 9. So if I just go back, my first derivative was the 9x squared minus x cubed. And if I factor that, I can factor out an x squared and I get 9 minus x. And so I'd have x equals 0 and x equals 9. I would set like x squared equal to 0 and 9 minus x equal to 0. And if I solve this one, I take the square root of both sides, and x would be 0. And this one I would add x, and x would be 9. And if I just check my sign chart for this, okay, all I care about is between 0 and 9 because that's my interval that they gave me. So I'm just going to plug in, let's say, 1 into my first derivative. And I would get 1 squared and then 9 minus 1. Again, it doesn't matter if you plug it in here or here. So I get 1 times 8, which is a positive 8. And so n is increasing. So you should check and make sure that your function is actually increasing. All of these, when I'm finding the point of diminishing return, should be, because the whole point is that my function is increasing, and then we're trying to figure out when it starts, the rate of increase starts slowing down. So when it says explain what the point of diminishing return means in the context, what we're going to say is that we know that we found, kind of the one before, we found that n double prime is positive. So my function is concave up on 0 to 6 and concave down from 6 to 9. So n double prime is greater than 0 on 0, 6. So n is concave up. And n double prime is less than 0 on 6 to, we just checked 6 to 9 because that's the interval. So n is concave down. And so what we're saying is when my function is concave up and it's also increasing, we said n prime is increasing, my function is increasing at an increasing rate. So since n prime of x is greater than 0 on 0, 6, n is increasing at increasing rate, which just means that my slope is getting steeper and steeper. And then on 6 to 9, again, since n prime of x is still greater than 0, and it's concave down, n is increasing at a decreasing rate. Okay, what that means is the slope is decreasing. The slope is still positive, so my original function is increasing, but the slope is decreasing. Okay, and just because of space, I'm going to erase my sign chart for now. And move this up. Okay, and so what the point of diminishing return means is when I need to actually move this, sorry. Is when the rate of increase is changing. And so when we have a max, so we were talking about the store invest X thousand of dollars. So at X equals 6,000 in an advertising campaign, and is at a maximum rate of increase. And so if we produced any more than n equals 6, then my output is starting to slow down. Okay, and so that's our point of diminishing returns. And then the last part just says how many televisions will sell at the point of diminishing returns, and n is the number of our televisions. So we would find just n of 6, which we did in part A, which is that 524. So we would sell 524 TVs. So that is the point of diminishing return. Let me know if you have any questions.